Professor Wang, are you ready?
Yes, I'm ready.
Oh, perfect. Okay. Yeah, we're going to go ahead and get started soon.
Okay, thank you.
Okay. If you want, you can go ahead and share your screen.
Sure.
And then I'll run through announcements real quick.
Okay.
Okay, great. Hello, everyone. Welcome to the final afternoon of the QSC Summer School. For this afternoon, we're going to have 4 talks from the Elmore Center. Our first talk for this afternoon is Professor Joy Wang. Joy Wang is an assistant professor of the Elmore Family School of Electrical and Computer Engineering and Weldon School of Biomedical Engineering by courtesy at Purdue University. She obtained her PhD degree from the University of Pittsburgh in 2019, and her advisor was Professor Heng Huang. Prior to this, she received her bachelor's degree in bioinformatics from Zhejiang University in 2013, and her research focuses on machine learning and biomedical data science. So without further ado, Professor Wang.
Thank you. Sorry. So is my audio okay?
Okay, we can see you now. Great.
Okay, great. Thank you. Okay, hi everyone. Thank you so much for the introduction, and I'm very glad to be here today to introduce our work in fair and explainable machine learning. So nowadays, machine learning and artificial intelligence, they're kind of buzzwords. So we saw them everywhere. So last year we saw the exciting news from Deepmind, where they designed the machine learning models to address a 50-year grand challenge in biology, such that their model can accurately predict the protein 3D structure. And also every day when we are browsing online, we will see if we go to Amazon or Netflix or Spotify and so forth, we will see recommendations showing that you may like this. And all of those recommendations behind them, they are the machine learning algorithms and AI systems. And also, if we go outside, we see the road, there are already autonomous vehicles driving on the road. So we saw autonomous driving cars, like buses and trucks. So they're already being tested on the road so that they can better serve our daily life and make our life to be better. And also in quantum field, of course, the machine learning models and artificial intelligence, they are also widely used, where, for example, machine learning models can help quantum device design optimization. So for example, what we can do is we can use the generative models to generate the topology of the data so that we can improve and the design optimization in a more efficient way. So despite that machine learning and artificial intelligence, despite that they are widely applied in our daily life and everywhere in the research community, one concern is that state-of-the-art machine learning models, they are still black boxes. So here we take action classification test as an example. So what we take, the model takes as an input is input images shown. We have 2 examples like this. And then the model will make predictions with regard to the 2 input images and showing that for the input images, what actions they are doing, the person or the people they are doing in the image. So for example, for the first input image, the model shows that the model saw 2 people, they are brushing their teeth. And then for the second image, the model saw that there's 1 person cutting trees. And all of the predictions, they are based on the black box of deep neural network shown in the middle. So the reason the model is a black box is because it contains lots of layers of nonlinear projections, such that it makes the model to be hard for humans, despite the experts or lay people, to interpret what is going on in this model. So despite the correct prediction of the action prediction, it's still concerning because we don't really know how the predictions are made. So in order to improve them, there are recently some of the explanation methods proposed to explain what is going on in this black box shown here. So for different explanation methods, they are proposed for different purpose, for different assumptions of the data, or different types of data, or different data structures. And all in all, for those different explanation methods, what we can do is, for example, for this task, we can get the explanation of what is going on in this model. So for example, when the model says there are 2 people brushing their teeth in this image, where in the image the model is focusing on to make such prediction. And then the explanation in the format of a heat map just highlight those two parts, showing that the model is making such prediction because the model is focusing on those areas. And similarly, for this cutting tree example, the model saw those two parts so that the model makes such prediction. And explanation help us really to better understand what is going on in this black box rather than just seeing layers of neurons in the architecture. So, and then let's also briefly discuss why explanation is useful. So why there are so many efforts that we need to put to make the model to be not only accurate, but also explainable. So first of all, this is what we already discussed. Explanation can help users to understand model, to understand why did the model make such prediction, not something else. And then the second is the explanation is useful because it can help troubleshooting. So especially in the case where the model does not have really good performance, it makes wrong predictions, then the explanation can tell us why the model did this and then help the, say, model designers or domain experts to fix the model or to do debugging. And also thirdly, model explanation can help us to do knowledge discovery. So for example, in many of the cases where in say physics or biology or mechanics, we're gonna need to solve say PDE or ODE functions, then what people use a machine learning model to do this is they will say collect a bunch of simulation data and then they fit all this input data into a machine learning model and then let the model to fit the output. And then if the model is able to approximate the output really well, then they will further explain the model showing in the middle to see in the prediction, when the model is making such good approximation, what are the features that are contributing the most to the prediction. And the features identified by the model explanation can help us identify the important features so that can help us to improve optimization and also screen parameters in like building the PDE or ODE solvers. So those are the use cases where we can make explanation to make the model better. But so despite all those facts, and so since everything is promising, model is accurate, and we have ways to provide the explanations, and the explanations can help us in all these different aspects. However, there's one fact we want to clarify is that when models are making predictions, they can make correct predictions, but the predictions can be made in a way that is totally different than humans. So here's another example of image classification. So for here, the model takes an input image, and then the goal is to predict what category does the object in this image belong to. So for this case, still a black box of deep neural network machine learning model, and the model says the input image contains a pufferfish. This is a prediction, and this prediction is correct. So this is indeed a pufferfish. But if we take a look at the explanation that are provided by the different explanation methods we discussed before, and showing that when the model is making the correct prediction, what regions or areas of the input image the model is focusing on is the three highlighted part. So in other words, it just means the model is making the right prediction by focusing on the three highlighted regions. If we map them back into the original image, they are corresponding to the color and edges of the image. So this doesn't really make sense to our humans, because if for human experts to conduct exactly the same task, they will be focusing on exactly the same different, object region, because they will be focusing more on the like say body or tail or color of the eye, something like that, to make the prediction. And another example of this observation where models can make correct predictions, but in a different way. So here we still do image classification, but we give the model a different task. So we want one same model to make prediction for two images. So it's the two versions of the same image, where the versions are corresponding to the original version and the version after a fine transformation. So for example, in here, we rotate the image counterclockwise and shift it a little bit to get the bottom one. And then we want the model to classify what object does this image contain in both of those two versions. So for the model we build, it is able to correctly predict both with respect to both two versions. So predicted class is shipped for both of them, and they are all correct. But if we take a look at the heat map, the explanation heat maps that we can obtain from the explanation methods showing why the model makes such predictions, then we can see that the model are making the correct predictions for the two versions of the images, but based on totally different mechanism. So when the model is predicting for this one, it is focusing on the main body of the ship. But when the model is making prediction for the original version, it is focusing on something else. This is also counterintuitive because if for us humans to conduct exactly the same task, we will address the same issue but with a different way, because we will be always focusing, say, on the main body of the ship to do the classification. So these are the observations, and then let's discuss why this is troublesome, why I need to address that. So given the observation that when models can make correct predictions, but in a different way than humans, then what will happen? So let's kind of rethink the three advantages we listed as why explanations are useful. So first of all, we said explanation is useful because it can help users understand the model. But if the model is making prediction in a way that human cannot understand, or in a way that doesn't really make sense to human, is the explanation still helpful? So still the parrotfish example. So for the parrotfish example, the input data, and we are given the heat map, we are given the explanation map of the prediction. So this does contain some information, but if we provide this to a human or domain expert to say, this is how the model makes the prediction, it doesn't really contain much meaningful information to human because it doesn't match with what we humans conduct exactly the same task. And secondly, previously we mentioned that explanation is useful because it can help troubleshooting. So still the same example, but in this case, we do some like minor tweaks to the input image in a human neglectful way. So if for our human eyes, those two images are the same, but we add some like neglectful tweak to the image down below, so that in this case, given this input image, the model will make wrong prediction to the input image. So the model will predict this input image as MACLIS instead of puffer. So this is a case where the model makes wrong prediction. And previously we mentioned that we can use explanation to fix this because it helps us to understand why the model did this. And we do get the explanations. So explanations for both correct cases and wrong prediction cases, they are both provided, but neither of them make sense. So if we provide this example, like this, all of the information, including prediction and explanation, to either a domain expert or to say a model designer, it's really hard for them to use such explanation to fix the model, to fix how can we make correct prediction for this guy. And then third, last but not least, is previously we mentioned that explanation is useful because it can help knowledge discovery. So let's also rethink what we mentioned of how we use explanation in this knowledge discovery part. Is we use the data, simulation data, to fit the model, and then we want the model to fit the output really well. And then after this, we will explain the machine learning model to identify the important features. And then based on this explanation, we'll just screen out other features and say these are the parameters we will get, and this can accelerate the optimization based on the machine learning models. But does the identified features by the machine learning models make sense to humans? This is a little bit questionable because those features identified shown here, they are definitely important to the model itself, but they are not guaranteed to be important to humans because models, they can fit the data using a totally different way. They can fit the data by fitting noise and fit really well. And if this is so, then the discovered image, the discovered knowledge in this case may not be that useful as we expect. So those are the concerns that we have based on the observations that we find that when models make predictions in a different way than human, then explanations may not be that powerful. Then what we do in this, I like to discuss in this talk is to propose some of our strategies to show what are the strategies we propose to address this. So in a nutshell, our strategy is to regularize the model such that the model can make predictions in a human desirable way. So our discussion will be divided roughly into two parts. The first part is to still based on the image classification test, such that we want to make sure the model explanation to have certain property. And this property is mimicking some of the properties when humans are achieving exactly the same task. And the second is more like a general way to use this regularization of explanation such that we can use this to improve fairness in machine learning model. So let's start with the first one, which is self-interpretable model with transformation equivariant interpretation. Okay, so again, this is our old example of the shape prediction data. So two versions of the data, and then we want the model to not only correct predicted them, but also be able to provide reasonable heat maps as we show here, such that when the model are making predictions, they are making the correct prediction and also based on the right reasons. The correct reasons means they are doing the same thing as humans, such that they are always focusing on the main body of the shape. In order to address this goal, in order to address the heat map we show here on the right-hand side, which is what we desire, we need two requirements for the model. So the first requirement is we need the model to be self-interpretable. Self-interpretable means the model needs to be interpretable by itself. The model should be able to provide a heat map like this by itself, without any further post hoc or other methods to provide the heat map, such that we will be able to regularize the heat map. And the second is we want to regularize the interpretation to have certain properties. The property we show here is the equivariance with respect to affine transformation. So affine transformation is one of the popular type of transformation we apply on the image. So it includes like rotation, like shifting, translation, or mirroring, things like this. And then what we want to do is Federated model. This is the rough idea Federated model where we build a model to be a deep neural network, but it is interpretable such that it can provide a heat map just look like this. And the heat map can help us, one, better understand what the model is doing. And second is to facilitate us to directly regularize the interpretation. And second is we add the affine transformation equivariance property, like constraint, into the model such that when the model is taking the two versions of data as input, it will always be focusing exactly the same area. And this is regularizing the explanation of the model such that the model can make not only correct prediction, but based on the correct reasons. Here, correct reasons means in a way that is similar to humans. And here are some of the results we get. So for all of the images, the model is able to correctly predict them, and also be equivariant with respect to such affine transformations. And also one thing interesting to mention is since our model is intrinsically a deep neural network, so it has really high representative power so that the model is able to handle the complex image classification tasks with high accuracy. So roughly it means the model is able to be interpretable while not compromising accuracy. So this is the first part. And then the second part is still working on the regularizing the model with respect to the explanation. And the goal is to make the model to work in a human desirable way. And in the second part, the desirable property is fairness. So fairness is a new concept. So for here, we like to show a brief introduction of what is fairness or what is bias in machine learning. So with the wide application of machine learning in different regions, in like criminal justice, in recruiting tools, in face recognition, image classification, and many fields like this, recent studies identify that despite the model seems to be performing accurately for these different tasks, there are biases from the models. The bias is against certain groups of people in a certain like demographic group, and the demographic group can be a gender group, race group, age group, or people from different geographic locations, things like that. Okay. So for example, in image classification tasks that we show here. So this is the action classification the example we used before. So for here, in this task, despite the fact that the accuracy of a state-of-the-art model is okay for this task, study found that there are biases, like gender biases from this model. So when the model is classifying or identifying what the person or people is or are doing in the image, if, say, the person in the image is a female, then the model is likely to mistake the person to be doing tasks like washing, microwaving, or cooking, even though the person is not doing such tasks. And also, when the person in the image is a male, then the model is likely to mistake the person to be doing tasks like shooting or like cutting trees, even though the person in the image is not doing those tasks. So these are the gender biases identified in the models, and this is concerning because this is not what we want in the model. This is not a human desirable property. So in order to address this, we need to go to explanation for help, because as we mentioned as the three advantages, explanations can help us better understand what is going on. So here's an example where we can use explanation to help us identify where does this bias come from. So we apply the explanation methods to find the heat maps of these images and found that when the model for these two models, they usually contain the gender bias. The reason they are genderly biased is because when the model is making predictions, they tend to focus on the facial or regions related with the person in the image. So for example, for this barbecuing example, the model tend to focus on the face of the person. So in other words, the model is more likely to first identify if the person in the image is a male or female, and then make the action classification prediction. So this is why bias is occurring in these images, because the model is using the gender information to make the action classification test, but it shouldn't. Then after we get this observation, so that explanation tell us like why the model did something wrong, then we'll be able to address that. So in our model, what we do is we can regularize the model so that we want the model to be focusing on the areas that are not gender related, but more on the part that are actually related with the actions. For example, still the barbecuing example, when the model is classifying what action the person is doing in the image, the model should be focusing on the part or the utensil part rather than what the person look like in the image. So in this way, we'll be able to address the bias to improve the fairness of the model while not compensating accuracy, so that the model can still accurately predict what the person is doing in this image, because we help the model to focus on the right part. And one other thing I'd like to discuss is that previously when we talk about explanation of models, all of the explanation examples, like the format of explanations, are in this way, like a heat map. So in roughly speaking, the explanations we get is we take the input image, and then the model will tell us that among all these input pixels, which pixels are contributing the most. Or in other words, if our input feature are not pixels, but other format of features, then what we are doing is more like finding what are the most important features, like individual features, to the prediction. So this type of explanation is called attribution. So attribution is definitely one type of most popular explanation method that we heavily use. But we want to note that explanation is not limited to attribution. So if we put the explanation of machine learning in a more general manner, then we can go much beyond attribution explanation to get explanations in a lot of other formats, and those format of explanations can be also really helpful for us to better guide the model to work in a human desirable way. Okay. So here is an example of explanations beyond attribution. So in this case, this is an example of a criminal justice data set. So what the model does is take the input data. So each input data is corresponding to one person, and the model wants to predict if the person is gonna commit crime in the future. So y equal to 1 means yes, so this person will recidivate it in future, and y equal to 0 means the person will not commit a future crime. And in this case, we observe that the traditional models, they tend to have race bias. So they tend to be biased against certain racial groups. But we don't really know why. So we want to provide the explanation. And in this case, the format of explanation is not what is the contribution of different features, but is with respect to the distribution of the outputs of the data. So what we do is we plot the output distribution of the model that is making the bias and see what does the output distribution look like. And the output distribution, we plot them with respect to different racial groups because the model, we identified racial bias from the model. And based on the observation, we can find that for groups of people, no matter they are committing a future crime or not committing a future crime, in both cases, the model is likely to give a higher risk score prediction. So in this case, to the righter hand side, it means the model tends to treat the model to have higher risk or more likely to commit a future crime. So the more to the right, that means higher score. And then in this case, the model has an obvious bias towards this orange group. In this case, orange group corresponds to the Black people, and a green group corresponds to the white people. So in no matter what group, the model always have such racial bias, and this is why the model makes the racial bias. So in order to address this, since based on the explanation in the format of output distribution, we get the reasons. Then if we get the reasons, then we can design the solution. So the solution we design is we want to adjust the classification threshold such that we want to adjust the cutting threshold. Cutting threshold means if risk score is higher than a certain value, then the model will predict the person to be a future crime. If lower than a certain value, then not a future crime. Then in this case, since the model contains an intrinsic bias towards different racial groups, then what we want to do is to adjust the cutting threshold for different racial groups. And we take the cutting threshold in the classification task directly into the optimization problem so that we can optimize the performance loss is with respect to the accuracy, fairness loss is with respect to how fair the model is. And we directly minimize these two losses with respect to the cutting threshold we find for each group. The threshold is used to compensate for the intrinsic bias that the model have in the first place. So this is another format of explanation in a general manner. And this format of explanation is also pretty useful for us to address like machine learning bias to improve fairness. And one other thing I want to mention is in this way, by adjusting threshold to compensate for the bias, we are not sacrificing model performance. So we provide theoretical studies to show that when we are doing this, even though our goal is to improve fairness, but we still have guaranteed performance with respect to the model performance, and our proof is with respect to the upper bound of the loss function values. Okay. So these are all of the things I want to mention in my talk today. And in conclusion, what we want to do is to show that, first of all, explanation is important. And second of all, more importantly, making or regularizing the explanation of the model such that the model is performing in a human desirable way is really important, so that we can better use the model, so that it can better serve our daily life and make our lives better. And this is important not only in like quantum field when we use machine learning models, or in images or natural language data. So everywhere when we are using machine learning models, we should be focusing on this part, use explanations to tell us why the model is making such predictions, and also use explanations to characterize the model behavior to be in a human desirable manner. And that is all for my discussion today. Thank you so much for your attention. I really appreciate the opportunity to share our work here.
Okay, fantastic. Thank you very much, Professor Wang. Great lecture. For the sake of keeping our schedule compact and moving forward, we will have to forego questions for now, but if anybody has any questions for Professor Wang, please feel free to reach out. Next, we have Professor Lam. All right. While everybody's getting set up, Professor Alam holds the J.N. Gupta Professorship at Purdue University, where his research focuses on the physics and technology of semiconductor devices. From 1995 to 2003, he worked in the Silicon ULSI group at Bell Labs, Murray Hill, New Jersey. Since returning to Purdue in 2004, his group has explored the reliability physics of nanotransistors, limits of nanobiosensors, atom-to-farm modeling of solar cells, and physics/technology of Landau transistors. Without further ado, Professor Alam.
A kind introduction and for this opportunity to be able to speak at this meeting. So last year, when an Intel CEO in their yearly presentation, Intel Lab presentation, predicted that there would be 100 billion transistors, 100 billion integrated circuits just from Intel alone in next couple of years. What he was really basing this prediction on, that there would be soon a smart everything future. The smart everything means smart agriculture, smart healthcare, smart energy. And in order to enable those sensors and process the data, that there would be many, many integrated circuits necessary or microprocessors necessary. And therefore, the hope, the intrinsic hope underneath that type of vision of integrated and smart everything is that one day soon, we'd be able to address some of the grand challenges that humanity faces, despite all the efforts that we have, all the science that we have. And one of those significant challenges is that the human population growth is going to go up by almost a third by 2050, and a significant amount of growth in food and would be necessary in order to support this human growth or this growth of population. Now, of course, the Green Revolution has been enormously successful. As we know, from 1960s onward, there have been a significant amount of increase in the food production in the world. But what we don't often realize that this has actually been achieved at enormous environmental cost. The picture that you are seeing here is the satellite picture showing the Gulf of Mexico, essentially covered by this waste from various farmlands, and especially this nitrates. It is destroying the overuse of fertilizers, are essentially destroying not only the drinkable water, but vast amount of marine lives and other things. And if this continues, then this is going to be a significant challenge that we'll all have to face, not in such a distant future. So the question when you ask that, what is it that is causing this trouble? You find out that this is a remarkable and very interesting answer. And the data that you are seeing on the left is essentially a a map of this various types of land in the Midwest, in America. And what you find that there are three types of land. One where the growth is very high, the yield is very high. You don't need a lot of fertilizer. Then there is another part which is sort of stable. But the third is actually a very poor quality land. The farmers actually put a lot of fertilizers in the system in order so that, because this is the land they have, anything that they get will give them the income that they need. And so therefore, people are putting enormous amount of unsustainable amount of fertilizers in order to sort of get some yield from the land. Now, being an engineer, of course, I work on these sensors that I'll be telling you a little bit later. But one thing I also work on, and that I've been working on for last 10 years or so, is a globe scale understanding of renewable energy, starting from the physics of nanosecond and nanoscale physics of solar cells, all the way to the kilometer length scale of solar farms by integrating the satellite data, the terabytes of satellite data from NASA satellites. There are about 11 of them circling on our head right now worldwide, 15-minute data that we were able to generate a huge amount of information about the potential of solar energy, by solar cells, photovoltaics, for different technologies. For example, you can see monofacial heat or bifacial, this emerging technology, tracking like sunflower, tracking the sun. So therefore, we can calculate these things. And as an electrical engineer, therefore, I was very excited to propose, among many other people, the following hope that to address the grand challenge that I just explained. That let's say there are soil data in terms of nitrate and others. And then there is this weather parameters from NASA satellite. And that we can integrate through an ag machine learning system because it's a lot of data. And we can make point by point prediction, kilometer by kilometer prediction worldwide that what would be the agriculture output at a given year for a particular type of crop, let's say rice or wheat at a particular point. And then I have the solar model I just explained to you, and we can combine those into a machine learning algorithm, this PVML. And again, one can do kilometer by kilometer resolution, the whole thing, and any place where it is not very profitable or where the fertilizers is being overused, why not give the farmers an additional opportunity to earn certain amount of money simply by putting solar farms over there? That is like a crop that does not require any fertilizer, and thereby we may be able to bend the curve in terms of this environmental factor, because these are globe scale solutions. Only then I realized that if things were so easy, this is where most of the time we would like to end the talk, saying that machine learning and other things can help us address some of these global challenges. But what I realized that the problem actually is not the end. This is where the problem actually begins. And rest of the talk will be actually about what problem we unearthed and what solutions we came up with in order to sort of combine this and make a dent on this problem. The problem actually is not with the algorithms. The problem is with the data. The beautiful pictures that we see here, let me see. The beautiful pictures that we have seen here have been generated by US Department of Agriculture over a period of 30 to 40 years, because at every point this soil sample was taken, send out data, hundreds of millions of dollars were spent to create a map which is sort of dead on arrival. What we need is a dynamic map that updates itself. Otherwise, how can you do real-time meaning monthly or yearly policy decisions about where to plant and how to invest in a given land, how to do it dynamically. So this is actually a fossilized data. Looks very good. It's fossilized. And the reason is that these data were sort of, as I just mentioned, were sent to the lab. very expensive equipment, essentially just like your blood tests. You send it to the lab, and then that measurements are done and the maps are created. So of course, then the next thing, what the Intel CEO scenario that I just told you about, would envision a smart future, a smart agriculture future where these sensors are distributed everywhere and essentially constantly sending data, and you have a dynamic map supported by these hundreds of millions of sensors worldwide. That's the vision. And how do you do that? Of course, you cannot put millions of these very expensive sensors in here. You probably want to do roll-to-roll or some sort of other inexpensive sensors. And the type of sensors these nitrate type of thing generally use, and I'm not going to go into the physics, it simply takes in that nitrate molecules and sees the amount of potential generated. And through a Nernst equation, it connects that once you measured the potential psi, it tells you at that point in the soil how much nitrate you have. The challenge is this whole scenario would not work. The reason it would not work is that when we send our blood samples or a soil sample from our garden to a lab, in a lab, this Nernst equation, there is somebody who is controlling the temperature of that lab, and there is a technician who every morning, he or she, every morning is calibrating the sensor by referencing it to the reference card. Throw it in a field, there is no control over the temperature. Morning and noon, summer and winter, temperature is all over the place. And then there is no calibration. Nobody is calibrating anything. There you cannot even put a battery inside, because the battery dies, then who is going to replace the battery of all these sensors that we are talking about? So this notion that you can just take something from the lab and put it in a smart agriculture, a smart transportation thing is a misunderstanding. It misunderstands the fundamental nature of the problem. So therefore, it actually turns out things are even worse. In collaboration with our colleagues from the Wind Center, once these sensors were actually implemented in 10 counties in Indiana, not only the sensors were doing all over the place, you know, this sensor 1, sensor 2, they were all over the place, fluctuating every few seconds with a orders of magnitude variation in analyte concentration. You couldn't possibly use this data for anything. No amount of machine learning is going to save you downstream, because the data itself at the source is corrupted. And then there is algae forming, films are drying out. I mean, this is a very difficult situation. So it turns out that you cannot really solve this problem just by doing downstream processing. If the data is corrupted, what I realized in our group was that actually you have to view sensors or semiconductor devices in a fundamentally different way. And the fundamental different way is to think about a sensor not as an electronic device, but as a communication channel where your input nitrate concentration is the message the ground is trying to send it to you. And the sensor is the communication channel, uncontrolled, degrading, temperature fluctuating communication channel. And you are getting a signal and you have to infer back what the original concentration must have been without any help of anything else. Somehow you have to solve this problem. In communication theory, we know that if you can map this problem, we can take a whole set of ideas from communication theory and apply to this problem. And that has to do with time redundancy, with space redundancy. There are multiple techniques that you can use. So we used a set of concepts from information theory and from biology in order to solve this problem. So I'll very briefly explain to you how this reliable sensing is possible with unreliable sensors. So it turns out that if you have two sensors, and in this case, poorer quality sensors are actually better. So that if you have a set of sensors who are not all exactly alike, that means that if you have sensor 1 that is following the Nernst equation with a variable temperature, and sensor 2 has a slightly different thickness and slightly different reference condition, It turns out, although individually you cannot really measure the concentration because the temperature and this degradation is happening, algae forming and drying out, the difference of the two, and here is the physics coming in to clean up the data, that the difference of the two turns out that it cancels because you are measuring the same analyte. It cancels the unknown N, and thereby it characterizes, quote unquote, the channel. It tells you, creates its own thermometer. It measures its own temperature, not by having an external thermometer powered by anything. This is a zero energy thermometer, which makes its own temperature measurement simply from the difference of the two signals. So this is a theory. Of course, we like theory people, semiconductor devices. So you can do that. But what we are very fortunate to see, that when the data came from the field, this was all over the place. And yet, when you take the difference of any pair of the signal, it exactly gives you the temperature, the unknown temperature that was sort of we did not know about. It gives you the temperature, and once you have the temperature, you can correct the signal, and the signal, once corrected, becomes much more stable. So what is the idea here? The idea is here, instead of one sensor that we typically use in our lab, when you send your blood samples there, they don't use multiple sensors. Here you use the diversity of sensors, diversity of poorer quality sensors actually to correct each other, self-correct, without any power consumption, and thereby get reliable signal from these unreliable sensors. But you see, even this is not the end, because here I have 4 sensors. 2 of them are saying that this is the analyte concentration, and the other one, you could ignore it. The other one is saying the concentration is somewhat different. Maybe because it was degrading. The sensor was degrading because it is underground, and therefore it could have degraded. It turns out then you can borrow. We are very good at borrowing. So you can borrow ideas from Facebook and the software companies, that the way they ferret out the fake news, we can use the same concept here. So this is the second strategy. First strategy is self-correcting temperature. The second strategy is that when you have degradation, you can use this. Assume that you have, for your morning news, you have 4 sources of news. One is reasonably reliable. Another is sometimes reliable, sometimes not. Maybe Fox News sometimes. Another one is always completely wrong, the red one. If you try to do a majority voting on this particular one, what will happen? That the one that is farthest from the truth will take over and essentially will distort everything. Conspiracy theory will distort everything. But then, even if you try to do majority voting, because you don't have a large number, majority voting will also be corrupted by periodic this type of thing. So the approach that we used is a Bayesian emule, where the historical credibility of a news source, and here the news source are individual sensors at the news source, the historical credibility of the source is used to weigh their relative contribution. So for example, at this point, the one that has told the truth more frequently will have a little bit more weight compared to the other one. And the ones that have always consistently said wrong things will not be given any weight. And so this is the algorithm we used, and they're calculated on the dynamic sliding window, this credibility index. And now you can see, with a sensor that costs a few dollars, can produce many more information, much more information, and yet can precisely reproduce the experimental results that are done in the lab that are far, far more expensive, at least 1,000 times more expensive. This principle that more is different is a very fundamental principle of physics. This is how a class of bacteria essentially, and these whole concepts I learned from quorum sensing. A class of bacteria actually can detect signals close to the fundamental limit, and yet there is no computer supporting this bacteria. They essentially learn how to do active averaging by exchanging protein information or molecule information among them. So this idea that more is different has to be a new paradigm in creating data from the sensors. So this is strategy one. And hopefully someday this type of thing, not today, but someday this map will not become a fossilized map. This map will become a dynamic map that is updated probably every 30 minutes, and real-time decision can be made. So now let me tell you the second thing about solar. You know, I just told you about agriculture, the problem with agriculture. Now let me tell you about the problem of solar cells, because that's the second part, right? I mentioned to you that there is all these predictions we made, takes a lot of time. Student took a year and a half to write the code, and these papers are probably one of the most cited in the field because nobody in the academia across the world can do this type of calculation. So we are very happy. We have big computers and big physics, so that's very good. But the second you want to verify these type of things, you get into trouble. The reason is nobody wants to share the data. Why would they? Because every time they are sharing the data, they are being exposed to a lawsuit because maybe their energy yield is a little bit lower compared to their competitor. And so therefore, they don't want to get into this trouble of sharing the data. So there is no data sharing. So if you don't have any sharing the data, how are you going to do this 500,000 pixel points in here? You at least need a couple of thousand locations in order to predict that what is the thing that is going to be energy output in Sydney, or what is it going to be in Michigan, or what is it going to be in Siberia if you put something over there. Is this just a colorful, beautiful map, or does it have any physics content in here? Is there any truth to any of these beautiful, pretty pictures? And it turns out that once again, physics can rescue you in a very unexpected way. First of all, once you look at this data and do machine learning, one thing you realize that the problem may be actually extremely complicated, but it really doesn't really depend on too many things. Only thing it depends on is how much light you have at a given point, what is your ambient temperature, and how cloudy on average is the sky. That is the information that this terabyte of data that I told you about is obtained from this satellite. So that's the data we download. And so the idea now, my challenge is that I will never have 10,000 data points to validate this model. I cannot train a machine learning system, and yet I have to demonstrate that what we are saying is correct. So here is how we do it. It turns out that the three variables I just told you about, GHI, ambient temperature, and how cloudy the sky is, there is a span. This span is across the world, that if you did have 500,000 points, then you would have this curve covered. But it turns out that you don't really need to go to every point in the world in order to map this, span this whole thing. You just need a few points so that each of those variables along the axis are properly sampled. So this would be importance sampling. Not all points are equal. And if you, in fact, try to make all points equal, that is what expands the machine learning to larger and larger systems. You need to sample less, but sample more intelligently. And once you do this k-mean clustering, you immediately realize that every physics problem for the globe has actually an equivalence class problem. That is, the weather of GHI, KT, and all those things combined makes Michigan the same as Sydney. And therefore, if you do one measurement at Michigan, you do not have to make any measurement, because for those combination of parameters, this is the same thing. And so therefore, if you do something in Alaska, you don't have to do the experiment in Siberia, because again, the equivalence class is the same. So all I need is 10 data points. 10 data points in 10 classes, maybe 20, maybe 40, that will do it. Turns out that even that 40 I could not get, because nobody will give you the data. Those people, you send an email, they say thank you. So what do you do? Then in that case, students need to graduate, right? So in that case, what you do is being creative. One type of people that are very good at sharing their data are the airports and the universities, because they want to show how good their data is and how their systems are. So all we did was to search Google, and Google has these data selfies. Airport is very good because next to the airport, you cannot put a wind turbine, right? Because the plane needs to land. They are very, they have many, Indianapolis airport, if you came through that, you would see that. So all we did is essentially find in open literature 10 airport data. Then we made another observation that West Lafayette in India in summer, it feels like Arizona, and Alaska in winter, it feels like Alaska. That a given location has this, because the sun is moving up and down, samples the multiple effect of multiple latitude. Using these two things, and with only 5 locations in the world, in the United States, you can predict 500,000 locations in the world, kilometer by kilometer, with less than 3% error. This is that thing. Just put 5 locations and they get the data from there. These are the airports. And from that, you can predict everywhere else what happens in the world. Because in these over a year, this United States actually has weather pattern that samples the world. And that is the insight, second insight that allows us to use small data, good data, in order to solve this data problem. Of course, this privacy problem is a big problem, and we are also working on this problem by federated learning and all. But often I have seen that sometimes these will be interesting directions that we'll be exploring. In fact, what we are doing, that many of those algorithms that people demonstrate are based on this handwritten digit problem. In fact, you can use the pattern of energy output at a given location as if it is a handwritten digit. And now you have 10 classes. So if you can classify them, any algorithm that works here will also work here. So we can piggyback on the beautiful work all of you are doing, and actually we can take this whole field forward just by sort of riding on the advance that we have been talked about. Let me wrap up. So I will wrap up with this one comment, and then we don't have much time. To me, Ptolemy, as you know, the 4th century, the art-centric, the astronomer who posited this art-centric worldview, is the original data scientist. Because this person, based on thousands of years of observation by the Greeks, everybody knew exactly where every planet is. And he came up with a model with cycles and epicycles that would explain the whole world and the night sky so precisely that if any of you are taking your child to a planetarium, the thing, that cylinder that moves and the little cylinder that moves at the end, on the very end, is exactly Ptolemy's model implemented for your. It is so precise that it is very difficult to improve on it. And therefore, it is highly accurate, but we know it's completely wrong because it was an interpolation problem. When you want to send a rocket to Mars, you cannot use Ptolemy's model. It will not go where you want it to go. You want physics model because physics model can extrapolate. There is, without this physics model, then there is no hope that it can go anywhere. So to conclude, what I would like to suggest is that connect it up with the Intel prediction, that what we are doing today in many of these conferences or meetings is thinking about how large data collected from all these places can, through a black box or maybe interpretable neural net, can actually predict something. And what we are doing, we are moving in Ptolemy axis. Engineering, however, often moves into Newton axis because you want to do a few experiments, dropping off an apple, find out the value of G, and thereby send a rocket because you know the gravitational constant G. Few experiments that unify the whole thing. And often in the real practical problem, you want to do physics-guided machine learning so that you have a best of both worlds. But what I told you today is that this paradigm is not going to work. What I told you today is that the data that are going to come out from here are going to be corrupted. There's no amount of machine learning is going to save us. What we need to do is to push physics downstream where the data is being generated and fix it there. And this is what, in fact, this person, many of you probably know, is a transformational person, Fisher. In 1920s, he posited exactly that if your experiments are bad, your processing cannot save you. So what I'm suggesting through all this is that we probably need to reread Fisher's papers and rethink about machine learning in a fundamentally different way. That's all I had. Thank you.
Thank you very much, Professor Alarm. That was awesome. Thank you so much. Next up, we have Professor Brinton. Go ahead and get him set up.
Okay, cool.
Okay. Professor Chris Brinton is an assistant professor of ECE in the Elmore Family School of Electrical and Computer Engineering at Purdue University. His research is at the intersection of networking and machine learning. His group develops data-driven optimization methodologies for communication and social networks with a particular emphasis on distributed edge intelligence. They investigate including fog computing systems, the Internet of Things, and social learning networks. Without further ado, Professor Brinton.
Thank you. Thank you very much. Can you all hear me okay? We're good? All right. Did you get that bio? Is that from my website? Or, awesome. Cool. Thanks. I don't remember sending one. So thanks, everyone. I'm Chris Brinton, assistant professor, Elmore Family School of ECE. So today I'm going to talk to you about some of my research in a domain called fog learning, which I've been working on since I got to Purdue in 2019, and I'm currently working on in a bunch of different directions from the National Science Foundation, Office of Naval Research, and also most recently DARPA, actually. So to understand fog learning, we just have to start with understanding a couple of concepts in network systems, and also a couple of concepts in machine learning, which together actually have a way to integrate and benefit from bidirectionally with quantum science. So let's see here. Cool. Okay, so talk about what is fog and what are networks? What's intelligence? Well, today we have billions of connected devices around the world. And it's exponentially increasing, literally exponentially increasing. The amount of data that's being generated by these devices is literally exponentially increasing. It's not just an exaggeration. You can look at the data and it's like an exponential curve. So we have an exponentially increasing data generation at the edge, meaning our devices, our smartphones, sensors generating a lot of data, smart vehicles generating a lot of data. Any kind of device today that's formulating what's called the Internet of Things, right? We just have all different things from smartphones to autonomous vehicles and microwave ovens that are actually connected to the internet, that are collecting data. So this data naturally is fueling revolutions in artificial intelligence and machine learning domains. And I'm not in this talk, by the way, going to make any differentiation between artificial intelligence and machine learning. So with this data, what do we want to do with it, right? In the machine learning community, we tend to use it to train large models, try to boost our prediction accuracy, try to understand the reasons that decisions are made. Ultimately, right, we want to have that in our hands as end users, which more and more means edge intelligence. We want intelligence at the network edge, intelligence on our smartphones, especially, as we're traveling around. We want product recommendations. We want intelligence in our smart watches, my Apple Watch here. We want to, this is giving some applications of this. In particular, these applications are increasingly data intensive, right? So they require processing large volumes of data that are generated over short periods of time. And in addition, they're very latency sensitive, right? I mean, there's a difference between detecting whether someone has fallen down, right, which needs to be done very quickly if you're in the bioinformatics domain, versus making a recommendation to someone on what movie they want to watch next, which is maybe not as latency sensitive. There's not a safety issue there, right? But we have to focus on how quickly these decisions actually get made, okay? And then we also have to consider what do the networks actually look like today that are connecting our devices, right? We're here at the edge of the network, but what is the infrastructure connecting us to the cloud? What does it actually look like? And more and more, it looks like a very hierarchical type structure. And this gives rise to concepts called fog networks. Okay, we call it fog because it's a combination of the edge, between the edge and the cloud. Right, so fog is like, what's between the cloud and us. It's, an analogy to that. Atmosphere and weather conditions, I guess. That's where we get the name fog networks. So you can think of a sort of a continuum, actually, from the things or the edge devices that we have here, whether it's smartphones or smart cars, connecting up in some kind of hierarchical structure. So your smartphone may actually be connected directly to a base station, right? If you're on a cellular deployment, that base station is in turn connected to the core network, and ultimately to some cloud data center somewhere, right? Where a lot of the intelligence traditionally has been done, right? We tend to do processing in data centers because data centers have a lot of computational capabilities, right? But there may even be more hierarchies involved, right? If you're talking about sensors in a field, they may be connected to drones, UAVs. The UAVs, a bunch of miniature UAVs may be connected to some larger set of UAVs, and even high altitude platforms connected to gateways. And we have today more and more, we're talking about leveraging PLEO satellites, proliferated low Earth orbit satellites, right? So if we have we're actually, in some cases, in really rural areas, and in some parts of the world, in third world countries, connection to the internet is provided primarily via satellite means, right? So we have all these different ways of accessing the core network, okay? So fog is really a way of describing this hybrid between the edge and the cloud, everything that's in between. And fog computing in particular looks at solving computing tasks, not just in the cloud and not just at the edge computing, but using all the computing resources that exist between, including the cloud and including the edge. Oops. Okay, so how do we do this? How do we do training? How do we do model training today? There's a new concept, relatively new. It's like 2017, 2016. So it's, I guess I'm dating myself here when I say it's new. There's this concept called federated learning. Okay, federated learning is a way of training models over a very simple network of devices. It's a very simple concept. So rather than sending all of the data, where traditionally we would take the data that was at the edge and we would send it to the cloud data center, and the cloud would then train the model and send the trained model back to the devices. Okay, you think of any machine learning task, right? Predicting, doing some object recognition, right? Facial recognition, like on Facebook or something, or Instagram, right? That's got some machine intelligence. What happens in that case, right, is that actually when your photo gets uploaded to the cloud, it runs a facial recognition software and actually gives you suggestions of who is in the specific picture, right? So this is that's the centralized way of doing model training. Move all the data to the cloud. That has a couple of problems, okay? One clear problem is privacy and security, because a lot of people don't want to share their data for obvious reasons, right? Today we have a lot of attackers and adversarial behavior out there more and more. Cybersecurity is a huge issue. So we don't want to move our data. If I collect some data on my phone, I'm reluctant to share it with cloud data center, have it uploaded. Additionally, there's another constraint, which is that costs, really communication costs and scalability, because of the volume of data that's required. Sending all of this data upstream to a cloud using this type of star topology, which we call it in the networking community, where we have a single center node connected to a whole bunch of devices, that's fundamentally not going to scale beyond a certain amount, right? When you have to send more and more data, if each device is collecting more and more data that needs to be sent and processed, eventually you're going to come to a point where you can't satisfy the delay requirements anymore, okay? So federated learning says, okay, let's not move the data at all. Let's let the devices keep the data locally and have them train local models, local versions on their own local data sets. So my phone trains its own image recognition classifier to classify, the people in my pictures. Your phone trains its own image recognition classifier. Someone else's phone does it. All the different devices do it locally because our phones today are actually somewhat computationally powerful, right? They don't have graphics processing units in them. They're not super powerful like a data center, but they have some capabilities, right? Have them trained locally, and then periodically what's going to happen is the server is going to take those models and aggregate them, okay? And aggregation is just a really fancy way of saying average them. Take them all up and find literally the average, because a machine learning model, at the end of the day, is actually a vector. You can think of it as a vector, okay? It's a vector of parameters. It's a vector of parameters that are then taken and used in a certain way to make a prediction, okay? Take all those vectors, all the parameters, hit the server averages them and sends them back down. Then the devices continue. Then they do their local processing again. You can think that the devices they're diverging a bit, right? Because they're learning specific to their local data set, which may not be representative of the entire global data set, okay? Process happens again. Synchronization happens. So the more frequent synchronization we have, the faster generally we're going to get to the globally optimal solution, the model that would have been gotten if we had sent all the data in the first place and aggregated at the server. Okay, but federated learning is really a very simple concept, right? Local model training followed by global model aggregations. Repeat. Keep going. So now federated learning, it can be thought of, I think, as a stopgap solution to this problem, where you still have this star topology and you still have devices sending their models upstream, okay? So sending a model is much cheaper than sending a data set because the model is a representation of a data set. It's a simplified version. But even models today are becoming large, very large. We're talking millions, billions of parameters sometimes of neural networks. And the number of devices are getting really, really large too. So eventually you're going to come to the same problem that you have when you're trying to send the data up in the first place. You have scalability issues, right? So it leads to three key challenges to this federated learning paradigm, okay? We have heterogeneity in resources. Right? Different edge devices are different. Training on a UAV or a drone that has a lot of computational power and that's meant to run complex processes, that's going to happen a lot faster than, say, training on my outdated iPhone 6 or something, right? They're fundamentally different in terms of their processing capabilities. So we have heterogeneity in resources and also in the data set statistics. Each of our local data sets are going to be different as well. So they each have different properties, and we have to account for that when we try to think about what the best way is to do this training in a global sense. No one of our data sets is going to be representative of the global model that we're trying to train. So heterogeneity is one property. Another property that's a challenge to federated setting is the topology. Okay, topology is a fancy way of saying like a graph connectivity. Okay, so what's the graph? A graph is, I'm not talking about a graph where we have lines on it. I'm talking about a graph of nodes and links connecting the nodes. Okay, so in this graph, the devices are the nodes, the circles, and the edges are the links, typically a wireless link, right? In this case, that's connecting one of our smartphones right up to the central server. So the topology of fog networks does not look like this kind of a star topology. It looks like this. It looks like a hierarchy, right? So this becomes very challenging, right? As we start to expand the number of edge devices we have, we get a scalability problem, ultimately. This is fundamentally not scalable, this federated learning setting. And the third one is actually related to that topology. That's the proximity between the different wireless devices, okay? The devices are differing distances from one another. So if we wanted to leverage some more sophisticated techniques and actually let devices communicate and maybe share data, that gets harder as the devices are farther away because it requires more energy to do that transmission. When you're on, your cellular connection, you're generally using more energy to do a phone call than you are when you're just talking to your local router access point. But that proximity varies as well. So different devices have differing abilities to actually communicate upstream, cost different amounts. So fog learning is trying to unify fog computing, which is that cloud to edge paradigm. Trying to unify that with AI and machine learning, okay? And actually creating a bidirectional relationship between them. So we have fog computing contributes to AI and ML because it allows more accurate representations of how model training occurs. And it allows us to really speed up the model training process and make it run at scale. So that enables innovations in AI and ML. And vice versa, okay? Innovations in AI and ML can help us with fog computing, right? Because like any other domain, fog can benefit from AI and ML because we can use AI and ML to predict certain aspects. We can predict when new devices are going to enter a network, when they're going to leave a network. We can have some sophisticated analytics on what the distribution of data looks like across different devices, right? So that's what really my research is about, is trying to unify these two branches. Okay, and I use the word orchestration a lot, fog orchestration. It's a nice word to use in a proposal, by the way. Talk about orchestrating things. So we want to orchestrate the fog computing resources to jointly optimize several metrics. Another nice phrase to use in the proposal, by the way, joint optimization. Tends to work. So jointly optimize two generally competing factors, okay? One is the intelligence quality, is how good is our resulting trained model that we're getting? And second is the resource efficiency. How many resources do we have to expend to actually get that level of a trained model, okay? These two things are fundamentally competing with one another. To get a better model, we generally have to expend more resources. But if we can understand that trade-off and try to optimize the trade-off, elevate that trade-off curve, we can get better results. Okay, so some design principles in fog learning, and there's a lot. It's a burgeoning domain. There's a lot of stuff going on generally here, but I like to summarize it into 4 different parts. So when we consider this, this hierarchy from the edge devices, whatever they happen to be, UAVs, smartphones, self-driving cars and tablets, and they're connected ultimately in some kind of a hierarchical structure back to the server. That's this upstream process here, okay? So one fundamental design principle is If you recall in federated learning, we had this star topology connectivity, and we said, let's have the devices train the model locally, but we're going to do the aggregation globally. Okay? So one fundamental principle is let's also take that aggregation process and distribute that too. Okay? So we distribute both the model update, the ML update, and the aggregation process that's occurring. So how do we do that? Well, we do that by introducing a concept of local aggregations. So we have devices that are in neighborhoods near one another, actually do an aggregation, either by electing some central coordinator among them, maybe a powerful device that can actually take all the models and do the aggregation, or by having it done in a fully distributed manner, using consensus-based techniques. This consensus over a graph is a very well-studied phenomenon. You have a given graph, and you have a bunch of different nodes that each have a certain guess of a true value. They can come to a consensus by iteratively sharing information and re-updating and resharing and re-updating and so on. And there's a lot of very beautiful and elegant theoretical results behind that. It's actually how Google ranks web pages, or at least a portion of their process of how they do it is actually by building a graph of web pages and finding the consensus of the importance scores amongst those web pages. So that's one principle. Second principle, which is actually needed for the first principle, is we're going to look at device-to-device communications, D2D. Okay, device-to-device is being becoming very prominent in 5G and beyond wireless technologies. 5G is out today, so now we as researchers talk about 6G. Some people are even talking about 7G already. So we can start talking about 8G today, maybe. I don't know. So, but device-to-device communications is becoming much more prevalent, particularly between machines, different machines communicating between one another, like different UAVs, say, collaborating or trying to learn something. But even our smartphones can, in some instances, directly talk to one another. This is becoming more and more prevalent. We can leverage D2D for data sharing. Okay, data sharing is helpful if we trust who we're sharing the data with. That's a big if, right? But if we do trust who we're sharing the data with, that helps because we can then build better local data sets for us to do the training on, right? We can, in essence, smoothen out the statistical divergences that exist across our devices. But not only data sharing, but also for ML model synchronization. So also taking the trained models and say, if we can come to a consensus in this room, maybe amongst all of our devices of a given model, right, and find the globally average, find the average model amongst all of our phones, and then send that upstream to the data center or something. That's going to cost a lot less than if we all just send our models directly upstream, right? Because we could just take one phone and use that to send it upstream instead. Okay. The third principle is to integrate protocols for resource allocation and ML training together. Okay, so traditionally, these are not thought of as two aspects that are done together. Resource allocation is a huge concept in the network community, where we talk about how do I allocate processing or communication resources to different tasks that are being done. Certain jobs get done on different nodes, and it's done in a certain way. And so I have to allocate a certain amount of bandwidth. I have to allocate a certain amount of CPU resource, so on. It's fundamentally, these become optimization problems. Okay. But we need to consider specifically protocols for resource allocation in machine learning training, or machine learning training tasks, and understand the relationship between allocating more resources to a given device, or if I say this device should crank out a few more local model training iterations, how does that translate to an expected improvement in the global machine learning model that we're trying to train? And the fourth one, which really speaks to the hierarchy, is that we should adapt the synchronization frequencies throughout the hierarchy. Because as we're distributing this synchronization process, we think locally we have a set of devices that have some local device-to-device topology. They synchronize locally. That happens here too. They synchronize locally. They synchronize locally. Then we have to do global synchronization somehow, right? So that has to occur upstream. So what's the parent node essentially of these different clusters? The frequency at which synchronization happens here probably is less than the frequency that it happens at this layer, which is probably less than the frequency that happens at this layer. And the frequency at which it's happening here, all the way up at the cloud, would be the lowest, right? We would want to do that very infrequently, okay? We should be able to adapt those synchronization frequencies throughout the hierarchy to meet the needs, to meet the resource allocation needs and the machine learning training task needs. Okay, so only 5 minutes left, okay. Some required research innovations, okay? We need to codify the fundamental relationships, okay, between fog computing configurations, so how the specific topologies of the fog networks look, the machine learning training performance, okay, so how do those two things affect one another, and also the network resource utilization under heterogeneity properties that exist amongst devices. So what that means is we need a lot of theory. We need a lot of fundamental theory that's driving an understanding of how different aspects of this problem are related to one another. And we also then need these adaptive orchestration methodologies to actually adapt the resource and processing utilizations throughout the network. That has to occur at the device level. Okay, the devices need to adjust their own local training process, like their step sizes they use in gradient descent, the amount of data samples they process at each iteration has to occur at the fog level, so at the different nodes throughout the fog hierarchy. So how often do they do an aggregation amongst the devices down low, and then even at the cloud level, right? The cloud's still there. We just want to use the cloud more as an orchestration mechanism and to actually do all of the heavy duty training. And finally, testbed evaluations. So we have a lot of ways of doing that actually here at Purdue. There's a lot of different test beds that exist. There's some in the lab that I use collectively with some other faculty in my area. There's also other test beds that exist, some actually in Discovery Park, some down in Indianapolis. The Indy 5G zone is down there, right, for it's actually deployment of a lot of 5G technologies and devices for Verizon and AT&T. And so that's available, to research. So we need to have these testbed evaluations, not only to verify that our methodologies work, but also to generate data sets for us to use, right? Because there's an interesting discussion brought up, say, in the panel, like, what are the standards that we use in different areas? We're talking specifically in the quantum area, right? But in the communications and the wireless area, we need some standard data sets to understand and actually test training of machine learning models. Okay, and so obviously I'm not going to go through all these details. I actually did have some examples of some work that we've done in this domain, and I even put up some pretty math equations, but I'm not going to go through them. The key idea of what we're looking at is we actually, similar to in the information theory community, we try to come up with fundamental limits, fundamental bounds. So we try to upper bound performance. This is really a measure of how good our given machine learning model is based on the parameters and also the given data set. And so what is the difference between what we have versus what the optimal model is? How can we understand that and upper bound that in terms of parameters of the system? And we can get doing that and actually carrying out that work, we can get huge improvements in conversion speed and also huge improvements in resource utilization. Another example, doing this kind of local synchronization. And I also even had an example here from some of my research in online education, which I know sounds like a very unrelated topic, but in fact, this principle of federated learning can be applied in other domains as well, like online education, where we have students interacting with learning materials and with content, rather than sending their data up to a server, which costs a lot, privacy issues exist there, can have their devices train models locally to understand their learning preferences, their learning behaviors, and then have the server do the aggregations and also the personalizations. And we've actually applied this concept to a domain called knowledge tracing in the online education space. And we've looked at actually building personalized prediction models for different student subgroups. Subgroups meaning different genders, different gender identities, where people are accessing the information from, meaning like what continent they're from. And what we find is that by accounting for these factors and individualizing the prediction performances through this federated learning framework, we can boost the prediction accuracy, particularly for underrepresented subgroups, and also reduce the variance in the prediction quality across the subgroups. So I write a lot of papers. I'm an assistant professor, so here's some papers that I've written. And so I thank you very much. I will end there, and thanks to all of my collaborators who, did a lot of the work. So thank you.
Fantastic. Thank you for that great talk, Professor Brinton. Next up, we have Professor Shakiri.
Thank you.
Professor Ali Shakiri. His group studies mutual interaction of heat, light, and electricity in micro and nanoscale materials and devices. Gaining a better understanding of these interactions directly assists in the improvement of device and circuit performance in applications such as energy conversion, computing, and communication technologies. A variety of approaches are employed in his research, ranging from theoretical modeling over Monte Carlo and FEM simulation to experiments. Without further ado, Professor Shakiri.
As soon as I find it. Good afternoon. Thanks for staying for the last talk. I'm going to talk a little bit about how AI used in manufacturing and hopefully give you some ideas what are some of the opportunities and challenges at the boundary between AI and quantum. Let's make sure I have the pointer. So very quickly, I start with a story. I came here about 10 years ago, and one of the areas that I thought is good to look at is we have a nice nanotechnology center. We develop state-of-the-art electronics and photonics. But on the other hand, this is not the area Midwest. We have a lot of industries. So the question is, what can we develop next generation of devices where we could be the center of gravity? And we identified early on applications in ag, food, healthcare require devices based on non-silicon printed type, very low cost. that currently are done at the university levels, proof of principle, but really there is no low-cost solution for commercialization. So that the goal is to do a scale-up and low-cost manufacturing of these non-silicon smart devices. Early on, we realized if your devices are cheap, but every time you need data, a graduate student should take a voltmeter and measure it. That's not very scalable. It's good actually to get the students out and do measurements, but not that much. We also learned that working with industry is important. Here I want to acknowledge my PhD advisor and postdoc advisors, Amnon Yariv and John Bowers. Both of them, while focusing on a lot of high impact research, always had an eye on how the research could be translated. So we started working with companies in order to test some of the devices. Four of my colleagues had a big role in the SMART consortium. And I guess I start with Dimitri Peroulis, the co-director. We started it together. Jan Alebak and Ashraf Alam were partners in crime since the beginning. And we also started working with Miko Chakmak. So one of the first things you need innovation is you need tools. And we were fortunate, we got resources through university to set up labs. We call it roll-to-roll manufacturing. It's like a way to print things, not that different from your printer at home, a little bigger, but to print functional devices and systems. And we have to do a lot of characterization because that's how we can understand how they perform. There is a large group of faculty that are involved. You go from the top to the bottom. They range from materials, mechanical engineering and chemical engineering, down to devices, networking, and more recently on the education and workforce. You know, often you see big view graph with big, lots of pictures. All you have to do go on the websites and cut and paste. That doesn't really tell you something about collaboration. The group we have, what I think I should say is that at least 20 of our faculty and their students are meeting on a regular weekly basis. That's what we need to build momentum. If you want to innovate in order to write a couple of papers, that's the effort of 1 or 2 students. If you want to bring commercialization, it really requires a longer term focus. So what is our goal is to bridge the gap. There is a lot of basic research. The valley of death, some of you may have heard about it, is to get impact into society. There is, it's very hard because at the beginning you can get funding through basic research, and here you have funding through, of course, commercialization. But here there is a lot of unknowns. One of the things we have done, the consortium allows us to test ideas and share some of the risks. But then quite a few of these projects, we were able to take it with our company members to an IP protected research so that they could follow even more closely where it goes. So some of the things we learned through this consortium, I think is valuable to see where is the role of the AI. So I'm going to describe one project which is related to a printed sensor for agriculture. Here you see the picture. This is printed using traces and then some membranes. These are ion selective electrodes, and these are optimized to measure nitrate in the water, which is a fertilizer, as Professor Alam mentioned, is quite important. We package them, we put it in the field. This is actually a picture of one of the farmers. This farm happens to be north of us, actually west of us, and you can see this is the place they have lots of wind turbines. And here are the sensors, and here is the home of the farmers, and you have to go over 2-3 miles. You need to set up the network. In this case, LoRa. Students have to get themselves wet. That's good when it's hot like today. And then eventually we have to do analytics. So you have to do fully vertically integrated from your device to the data. What are some of the things we learned early on? If you take this set of printed sensor and you image them, they look similar, but also they are all slightly different. We take an array of 30 of them, we put in a solution of a known nitrate solution, and over 40, 50 hours, they eventually converge. and they measure, you get a voltage out. It's like a tiny battery. That's how this type of electrochemical devices work. And the voltage is proportional to the concentration. But you see there is a variability here on the order of 30%, and 30% or 30 milliwatt in this type of concentration means about a sensitivity of 30 parts per million. So as fabricated, there is inherent variability. Why? Because we used a low-cost solution, which is printing at room temperature. How would you make it more uniform and more predictable? A good manufacturing person says, let's, instead of printing in air, let's put it in a vacuum chamber, let's do evaporation, much more precise. Of course, that's an easy way to control the morphology, but then inherently become more expensive. That is challenge of manufacturing. Manufacturing is art of making things possible at the cost that people pay, not at any cost. Unless you work for NASA and they pay you $1 million for each devices because it has to go to outer planets. One of the interesting areas that we were lucky is working with Professor Jan Alebak and his experience to the Hewlett-Packard Printing Center. He said, let's us analyze the images of these devices and see if we can predict this variability. The fact that when you put devices in a solution, they logarithmically saturate actually can be demonstrated using theory, and that's what Professor Alam did. But the shift, the DC shift between devices is a complex function of the thickness of the dielectric coefficient as well as diffusivity of the ions. You cannot mathematically model that for these type of strange shapes, but machine learning and looking at the images, here this B factor, this shift, you can see the prediction versus ground truth. You can correct for large fraction, about 80% of their variability, and that's how you can get devices that are much more precise. So here is an example where machine learning and data can be used to improve manufacturing. So what one of the areas when you can take it further is to use, for example, the quantum classifiers to do image classification, to do even more elaborate areas. So this is one potential area to think about. Imaging can do a lot in the area of manufacturing. Professor Alam already presented this, so it saved me time. I can skip here. There is a big element of how these sensors actually perform in the field. Temperature varies. This is last July. It was days hot as today. And you see temperature goes between 70 to 100 Fahrenheit. The response of the sensors in the field, this is the apparent concentration. And you wouldn't expect concentration changes by 2 orders of magnitude between day and night. This is really a factor we did not anticipate. But if you take this variation out, the fact that it goes down in the middle of the month, it actually matches the time we had lots of rain. And when we talked to our agronomy colleagues, they said that's the kind of thing they expect. You dilute the water that is coming out. Of course, you should have less nitrate. We had students going and take samples from this farm, and our sensors package size cost is about $5. The commercial ones that are not continuous and point measurement, and you need a graduate students to go and do this measurements, is about $1,000, showed that we are off, but we show the trend quite well. So this was one of our first data showing in field using printed sensors. Quantitatively still off, and I think Professor Alam already showed, if you have multiplicity of sensors, here in this case, you have 4 sensors in the same location, 2 of them fresh, 2 others a little older, and the older sensor, after about a week or 2, they become temperature sensitive. Why it takes 2 weeks? Again, we still don't know all of the details, but the good thing about physics-based model is you can correct for that and basically show the black dots are measurements that are optimized based on, calculated based on the 4 experimental sensors, and the red points are ground truth. So we have a sensitivity on the order of 3 parts per million in a completely outside environment. So this is give you again ideas that Data can help you make the sensors more reproducible, and data can help you, once you put it in the field, to correct for aging and other factors. Now I want to switch gears. It's late afternoon, you may be tired. So if you were asleep up to now, you wake up, you wouldn't miss anything because this part has nothing to do with the first part. I'm going to talk a little bit about bigger problems. We have a challenge in US. This graph shows between 1988 to 2018, the US trade balance for advanced technology products. And you see up to 2000, we were a big exporter. And we have since then have become a huge deficit in this area. So that's one. We are not making as many high-tech things here, and that's not a surprise to you. Here is the workforce working in manufacturing in US. Between 1965 and 2000, it was almost constant, about 18 million people working in manufacturing. By the way, between 65 to 2000, population of US increased significantly. The fact that this stayed constant, that means fraction of jobs in manufacturing was continuously coming down. But that wasn't even bad enough. Between 2000 and 2010, we lost about 30% of our manufacturing jobs. And this has had a little uptake. If you look at more data up to 2020, 2021, we haven't recovered to the level we were. So we are really missing some of these. We had a project about 4 years ago, started looking at the 10 counties around Purdue. For those who are not from here, Tippecanoe is where Purdue University is, and the 10 counties are around us, so neighboring Illinois here, and going probably halfway through to Indianapolis, and about half an hour north toward Chicago. So these are the 10 counties, and the idea was, there was a foundation, Lilly Endowment. They said, we want to make this region prosperous. What is the asset in this region? We have a Purdue University in the center, and we have lots of farms and lots of manufacturers in this region. We have about 4,000 farms and about 250, 300 small and medium manufacturers. Here is a little data to show what is the population. In this 10-county region, close to 400,000 people, so it's really quite small. Half of it is in Tippecanoe, which is where Purdue is. The other half is the other 9 counties. You see it's very rural. That's where a lot of farmers and the small manufacturers have been living for a long time. You look at average employment rate for our region comparing to the rest of the state, comparing to the US total, you see unemployment was low in 2000s. We had this big financial crisis, 2008, went up to 10%, now back to the same levels. One of the lessons is statistics, when you average things out, may not give you the full picture. You look at this graph and you say, well, this region is like the rest of the US, New York, what's the difference? Averages are the same. What you don't see in this is what have happened within this region. Here is the graph between 2000 and 2018. The US population increased by 15%. Indiana population increased by 10%. So first of all, we do have movement to the two coasts. The center of the US is not growing at the same level. But if you look at Tippecanoe County near Purdue, students here know how many new buildings are built in the last couple of years. The population increases 30%. We think this is thriving location, everything is good, and it's true here. But all you have to do, look at the 9 other counties. They have lost 5% of the population. 5% of the population, you think numbers, that's really is huge financial problems for local communities. So the question is, some of the things we do in the high tech to make new product, can it help small and medium manufacturers? So we started this project. This foundation was generous, gave us $20 million for a 5-year project. And in these 10 counties, we identified a range of companies. Subaru is here, Fratco, some of you know, some of the food companies here, Caterpillar and so on. So we had so far about 70 projects with 27 of these manufacturers. And the projects are simple, installing sensors. Some of you recognize this neural network. Once you have data, you can do some interesting wonders, develop dashboards. When we started doing this, first we noticed two things. A lot of our small and medium manufacturers, they don't have the latest data tools. They don't know how to deal with their data. And the way we were working with them, which is one by one, helping them install sensors, that's not scalable. Somebody give you money, you put students to projects, that's good. But we need to think a little more fundamentally how some of these could be applied to them. Here I want to present it slightly differently in the sense of we think of data revolution is a continuation of what happened before. Let me tell you the 4 industrial revolution. Everybody knows Industry 1.0, when the introduction of steam produced mechanical boom in 1784. The Industry 2.0 is mass production. A lot of you know about Ford mass production, but if you look at here, it says the first mass production is 1870. Anybody can tell me what was 1870, what happened there? You don't have that many people good in history? Yes, trains? Well, maybe there's coincidence. No, trains was a little earlier, but has nothing to do with mass production. This is, yes? No, automobile was 20 years later. That was the real challenge is this. Automobile learned from this industry. 1870 is the first mass manufacturing slaughterhouse in Cincinnati. They learned how to cut meat in a precise way quickly to get meat out. And that's how Ford later learned how to develop the assembly line. Then we had computers in 1970s, and then everybody talks about smart factories now. You look at this graph, I think this is actually misleading because it shows you some automation with some data. And what you heard during this week, data give you wonders, make wonders. That's only part of the truth. If we only add a little data and make this efficient, that's not the full power of AI. And what I mean by is the following. Here is Business 101, value provided by number of users. Every traditional business, you look at Marriott, Hertz, and so on, you get more and more people in your company. The value you add to those people, you saturate. You cannot give them more value because you need more capital, you need more services. Airbnb, Uber changed the dynamics because the more users use their app, the more data they get, they do more things they could do. So the value can go up. This is what is called digital operation system. So if you want your AI system to be on the business side successful, you should think about this requirement that with number of users, scalability should not be saturating. There are 3 parameters required for that, and there is based on the case study at the Harvard Business School. You need to have scalability, scope, and the learning. What the scalability means is basically the network effect. When you get more data, you can use it for more easily, you can gather it. You don't need to hire 10 more employees to get 100 more customers. Scope is when you learn from one field to use it in another field. Uber was to go from one place to another. Once they knew the pattern of where people were going, they used that data for many other things. This is where the data keep working. And the learning is the feedback loop that is required for the other 2 to move out. So what does it mean in manufacturing? So we started a project about 2 years ago. It's called Future of Manufacturing, together with a couple of colleagues at Harvard, at Tuskegee Ivy Tech, and we have a planning grant for a center about this, together with UMass Amherst, University of Michigan, and UCLA. I just have 2-3 view graphs to tell you what is our motivation and where we want to go. So again, what has been done, IoT sensors and smart manufacturing have helped big manufacturers, but there is a key bottleneck. AI revolutionized many industries. The manufacturing challenge is limitation of training to in-company data. That's what I mentioned in the panel we had this morning. companies are not going to put all of their data in the cloud. There is also diversity of manufacturing platform. The same cutting machine can be used in so many different ways that you just take data from that machine and you upload it in a big server. Whatever AI algorithm you do, because it's used in different cases, you cannot really learn something new. So how to provide context is important. And finally, privacy and confidentiality data. So the goal we are saying is economy of scale without concentration. Basically, you do data aggregation to bring the cost down. And for that, you need manufacturers to work together in some sort of a co-op. And the goal is achieve that through secure data sharing. So the solution we have is to develop an AI commons. And some of the elements of it is you need to have edge analytics, because there is no way you can take your data all the way to the cloud. It just takes too much bits and too much communication. Tiny ML, tiny machine learning is an area that could benefit. We need to use some of the distributed algorithms, such as what Chris Brinton just described. And we also need to consider AI and worker user interface. Of course, anything we do in manufacturing is not at the top level only. We need to translate it to workers. So we are working with our local community college to take some of these in their new curriculum. Maybe the last, so our vision is democratize the human-centered AI solutions at scale to facilitate the resiliency and competitiveness of the US ecosystem, manufacturing system. This is a wicked challenge. It has both technical and human challenges. I already described this in terms of sensing, reliable sensing in unreliable environment, in terms of machine learning challenges, and as well as culture and confidentiality issues. And AI Commons for us is a way to see how we can implement this by manufacturers sharing data with each other. So what I want to do is, so that I don't bore you with just view graph. Oops. That's a little, let's see. Doesn't want to cooperate. Yes, let me go to the summary. So you already know Moore's law have changed computing, communication, and imaging. There is opportunity to take that to ag, healthcare, and disaster response, enabling but very low-cost sensors. In order to do that, we need a new manufacturing platform, and their machine learning could play a big role, and hopefully some of the quantum algorithm and quantum ways of scaling with the data could be beneficial. And you saw also how similar AI in manufacturing could be done more broadly for other manufacturing applications. I'd be glad to answer any questions.
Thank you very much. Thank you, Ali. We do have a couple of minutes, and why don't we encourage the audience ask questions not only to Ali, but also to previous presenters. I think we can take a couple of questions now. I think everyone is waiting for reception.
Yeah, if you can only go to reception if you ask questions.
Yes. Long way.
Hi everyone. Good afternoon. I want to ask the question actually to Prof. Christopher Brinton, the previous speaker. Okay, so you spoke about federated learning and fog learning, and I just want to confirm because I recently did some reading on federated learning, and actually a way to create tiers in the different, so rather than just aggregating all the models together at the cloud, aggregating it layer-wise. So, but then your approach with fog learning, which is, okay, taking the fog topology and using it for federated learning, sounds nice, but I was just curious, wouldn't it bring a lot of communications overhead and other overheads that would probably reduce the efficiency of the whole model?
Thank you so much for the question. If I can maybe restate it, just to make sure I understand. The question is around talking about one of the motivations behind this fog learning paradigm was actually to be able to scale up training across fog computing systems as opposed to the federated learning star topology. So, and the question was almost like it could introduce a lot of communications and overhead by doing that. And you're absolutely right. It definitely could, and that's a factor that needs to be considered. So in certain instances, it may actually make sense to default back to that star topology, fog computing. It may make sense, especially if we only have a finite number of devices. Well, of course, the total number is always going to be finite. But if it's a relatively limited number of devices, may make sense. Let's just do the aggregation in the standard way. Let's not introduce any of this additional overhead by local communications. In other instances, though, when you actually have a very disparate connected network, right? So you have different nodes, different clusters all over the place, all around the world even, right? Having them all be communicating to this central location can actually cost more than having this local communication. So it's that trade-off needs to be considered. You're absolutely right. Yeah.
Thank you, Chris. Thank you, speakers. And yes, Gerhard. We are asking more questions at the reception because we have an honor to welcome a very, very special person to conclude our school. And I think that I challenged Wikipedia to introduce you.
Say it again.
I will challenge Wikipedia to introduce you. So I'll try.
Oh, okay.
So,
Wikipedia.
yes.
Gee, you're right. The bastion of knowledge and truth.
So
Yes.
remarkable scientist, brilliant engineer, educator, technology entrepreneur, university leader, foreign policy official. You have been with former. Well, you've been with the Office of Science and Technology and advising Secretary of State, Executive Vice President of Purdue for Strategic Initiatives, John Edwardson Dean of the College of Engineering, and our most beloved and visionary leader.
Oh, thank
Dean
you so much.
Mong Chung.
Thank you so much. Is this working? I don't need it. All right. That is embarrassing. So now I don't know what to say. Thank you so much, Sasha. I could actually return the favor by giving the Wikipedia entries of you, right? So then that would be much longer and actually much more meaningful. As they say, those who don't have a whole lot to show will accumulate a lot of titles. So as you can see that I'm a collector of titles. But haven't done really much at all. However, I am just delighted to be here. This is a huge auditorium. It makes me worry about student-faculty ratio at certain introductory courses, especially to have a chance to talk to the quantum summer school. I tremble at the thought of speaking to quantum scientists and engineers, because when I was an undergrad at Stanford, it was 1996 or 97 that I took the quantum mechanics course from Professor Laughlin. And you might recall that he ended up getting a Nobel Prize in physics that year for fractional quantum Hall effect. So I thought, oh my gosh, I'm learning quantum mechanics from Professor Laughlin, the Nobel laureate. And the best part is yet to come. Around Thanksgiving time, he told us, you guys are very lucky. I'm not going to give you a final exam because I don't have time to write up exam for you guys. I have to busy prepare for my Nobel Prize speech. So I was relieved. And my education in quantum was destroyed at that moment because I was usually only waiting until the last week to do my study. So he told us this Thanksgiving time, Stanford's quarter system exams is 2 weeks later. So I stopped studying quantum. And I didn't start anyway. And then we asked, so Professor Laughlin, congratulations again. What about our grades? Some of you just got grade appeal emails from students, I'm sure. What about our grades? So Bob Laughlin said the most wonderful thing in academia. You all get an A. You all get an A. And I was like, phew, that's it. I'm out. I'm not going to spend time studying quantum mechanics. So to this date, I tremble at the thought of going to a room filled with the most distinguished quantum scientists and engineers. Oh, by the way, to finish the story, you see, this is a disorganized closing remarks. But so one kid next to me raised his hands. He's the, the annoying type, right? And he said, Professor Laughlin, but I was expecting an A+. We were almost about to smash his head and say, shut the heck up. We all got a free A. What do you mean, the A+? And then Professor Laughlin said, well, this is a socialist class. If you want an A+, you go to a capitalist quantum mechanics class. I don't think he is a socialist, but anyway, so I got an A in quantum mechanics from Professor Laughlin without knowing a thing about quantum mechanics. However, I do understand the importance of quantum science and engineering. So thank you to the Purdue Quantum Science and Engineering Institute, to the leadership here, and to, of course, Oak Ridge and the entire QSC leadership there. Thank you so much. I want to thank all the government agencies, to the private sector, and to our distinguished academia collaborators in the US and also elsewhere for giving Purdue a chance to host this annual, I guess, second in a row now, in person now, summer school. And I hope the past 4 days have been a productive one. You were all trapped here. You wouldn't know it was very hot outside. And we always celebrate because we only got 3 nice weather days in Indiana every year. So you just missed the 3 nice weather days. But I'm sure you gained a lot by learning from each other. And one thing I was hoping to convey here is just how important it is to the strategic initiatives at Purdue University and certainly to the College of Engineering. And I assume to our sister college in College of Science and other parts of the university as well, that the future of quantum, we hope that Purdue students and faculty will get to play a leading role in, along with all of the collaborators. I've learned quite a bit from, I see a lot of our ECE colleagues here. I see our distinguished visiting professors here about the role that quantum is going to play in control, in communication and computing, in security, in speeding up how we do AI, in rethink how we communicate in the first place. And I know that there's a distinction between the science and the engineering, right? Between discovering truth and between that and problem solving or making artifacts. But it's a unique strength at Purdue, I think, where we've got science and engineering faculty working so closely with each other, at least in this field. And it's a unique strength that we have both scale and the pinnacle of excellence. Some of you have heard me saying this for like 4 years nonstop. So you know this is coming. It's part of my blood now, that the pinnacle of excellence at scale at Purdue. So the College of Engineering, I have to brag about this because it's bragging about our faculty's excellence. Its graduate program ranking is now top 4 in the United States, 2 years in a row for the first time. We have by far the largest top 10 engineering program in the United States. and a top 3 online engineering program in the country. And that's because of the outstanding faculty that we have here. And when we think about some of the key initiatives, a lot of those are at the interface between the virtual and the physical. Whether it's modeling, a simulation, or is control, and we are looking at the atoms and the bytes meeting at an interface, and the quantum version of that virtual physical interface. And it flows both ways, virtual to physical and vice versa, in multiple factors. That is something that we are going to continue to invest. And part of that will be the physical space and facility needed. I didn't bring my checkbook. It's not a big checkbook anyway. So, but we are working with the university as a whole and our partners looking at that. And thank you for the outstanding leadership that Ali and also Ji-Hong in leading the Berkeley Nanotechnology Center so outstandingly well. And we're very grateful for that leadership. And we have a lot of potential in faculty recruiting. So I hope Sasha and Vlad and all of you have identified who we can steal away from other institutions in the US or outside. And we want to steal you in a variety of ways. You can be a visiting professor first. You can spend a sabbatical here first. You can bring your students here first. But that is the only thing that matters in the end is how can you steal? I mean, how can you recruit and retain and reward and support the talented faculty member? That almost is, I can't say that's the only thing that matters, but let me just say everything else is of measure 0 in the excellence of a university. Because with that, everything else will follow. So we will invest in facilities, we'll invest in the human talent, we'll try to innovate and try to partner with all of you. Now, if you are wondering, when is this guy gonna shut up? It's coming. Now, one last thought I hope to share with you is that as we think about the impact of quantum to everything we do, some of which are happening already, some are further down the road. And once I had a conversation with a MIT colleague, and he's a specialist in on the theory side to prove things that you cannot do with the things that you don't have yet. So he proves the outer bounds limits for what quantum computation can do. So I keep asking him, so when am I going to get a quantum computer? You know, and so on. He says, well, first of all, you are asking the wrong person. So I'm a theorist. And in theory, there's no difference between theory and practice. In practice, there is. So I don't know. You go ask somebody else. So I ask other people. And the most inspiring answer I got actually was, it's not just about when can you get that many qubits in whatever physical manifestation. It's about the process between here and there, and every time we take a step, we're learning new things about the physical phenomena and how to harness that. So it's not just putting a person on the moon that happens to be Neil Armstrong first, but is the process along the way that actually has so many unforeseen byproducts to scientific inquiry. And furthermore, he said, Meng, you don't know, quantum is bigger than quantum computing construction. That is a key part of it, but there are many other things. Here's a startup company already doing, quantum key distribution. And there's another large or small company already doing quantum sensing. So it is way bigger than that singular pursuit, although that is an extremely important pursuit. So I just want to share with you that we are keenly aware of the intellectual vibrancy, importance, and diversity of different types of topics in quantum. And we hope that we can pick the subsets where Purdue quantum science engineering can be the best in the world and collaborate with all of the others in other areas. What I originally planned to do is to learn something useful, actually, since Laughlin didn't give us the chance. So if you have a few minutes, I'd love to hear your observation. Any questions you may have, any recommendations to me? Like, Hmong, do not hire anybody doing that work. Or, I'm available. Any observations you've had over the past 4 days? And I know some of the topics, I see Chris over there. Congratulations on many, many young investigator awards. It's a monopoly, so probably illegal to get too many. But we would love to hear from you on observation on other related topics. May not be exactly in quantum, maybe on the workforce. We all know how important that is. The ultimate supply chain is human talent supply chain. And the scale and the excellence at Purdue, we hope will play a role in that. So any observations, please? Yes, please, Marty. When can you stay here forever?
Tell you what I think. Okay, this interface between information sciences, people like you, people from AI and quantum, it's a new field that there's almost nobody there. The techno, and this was some I suggest we do. Take a few people that are very good in, let's say, information theory, in the style of people like, Will Spoor and others that you know. Send them over to work with people that do quantum information right now. For example, in Germany, there is a guy by the name of Ignacio Cirac. He won the Wolf Prize. And he is probably the best theorist today in terms of quantum information on the physics side. Send them to learn the physics side, not the Shor algorithm, not this, but learn. And then you don't need to know really deeply quantum mechanics for that, but you need to know the aspects that will influence that and construct a new field of quantum information theory. It's not there. Quantum control, only physicists do it. Engineers don't at the moment. Pick a few of them, send them around to very good centers, and then get them back as assistant professors. That's my suggestion.
Okay.
We did that just now at the Technion with one guy in quantum information theory, a field that is just big.
Well, thank you, Marty. At Princeton, where I worked 14 years as a faculty member, we did some of those investments. And of course, we all talked about you all the time. And it turns out that my almost next door neighbor was the co-recipient of Laughlin's Nobel Prizes, Dan Cui, who's in the electrical engineering department, not physics department at Princeton. I guess he didn't do super string theory, but we were focusing on a bit of that. And my co-advisor, the late Tom Cover, the late and great Tom Cover, did some work actually with Yamamoto and others at Stanford on quantum information theory. Because of my utter lack of training in quantum, I didn't work with him on anything related to that. But I agree that part of that interface between virtual and physical is in that regard, right? And then there's also the part as a computational, maybe AI data science driven, maybe a numerical optimization driven way to look at quantum device design and so on. Actually, my other co-advisor, Stephen Boyd, did quite a bit of that, more for conventional optical devices using optimization to give weird shape that no one could have foreseen before. So that would be part of it. But I agree that another part of that interface would be the quantum information or quantum control theory. I think it would be great to see, especially quantum control theory, because at least classical Shannon information theory doesn't have a time domain prominently featured, whereas control is all about time almost. So the impact of quantum in the time aspect of control theory, that could be very interesting.
3 years from now, these will be the tools. Now is the
Yes.
time to invest some of the young guys that are about to graduate, send them to centers there, and teach the quantum part. They will know the information theory and the control they already know. So we need
Quantum Shannon, right? Or quantum Bodhi. Thank you, Marty. Yes, Wang, please.
Yeah, thank you for coming to give this closing remark. What I want to ask is, we have very good collaboration between science and engineering in the PQSER Center. And I just wonder what you can do, what else you can do to help elevate the kind of collaboration we have between science and engineering. Have you ever thought about that?
Right. I think chemistry, chemical engineering is another one. We don't have as much as we could have. And then there's the computer science, computer engineering part. Is actually a bit of a hindrance occasionally in recruiting faculty. They are a little confused as to which one do I go to and so on. And the ideal answer would be, it doesn't matter. You come here, do your good work, you have access to the top PhD students from wherever departments, and your outstanding course can be cross-listed to fulfill multiple degree programs requirements and so on and so forth. And you can go to 3 departments, faculty meetings, and have nonstop meetings if you want. So the ideal answer should be, it doesn't matter to the talents, students and faculty we want to recruit. We are not in that ideal state. However, I really appreciate how the Quantum Science Engineering Center has demonstrated the feasibility that it is doable, and we'll look into how we can replicate that success in that model.
Hi,
Yes, please.
I'm a grad student from Duke. I also went to Princeton.
Okay, great.
I just wanted to add, first,
A lot of Princeton people are now here, so maybe you can leave Duke and come here.
hopefully graduate first. I really enjoyed the Quantum Summer School, and this was the first of this kind that I'm attending. So I just really enjoyed everything here. One of the things that I enjoyed most, which was not part of the schedule, was actually a lab tour. I met someone here, and we decided, or we realized that we do similar research, and that was one of the things that I enjoyed most. And if in future, I know it's not easily scalable to organize lab tours for everyone, but I think it's a great way to learn about what other people are working on and exchange information.
Great.
Yeah.
Lab course. Where?
Lab tour.
Huh?
A lab tour.
A lab
like
tour.
touring their lab.
Okay, which
Yeah.
lab did you tour?
I don't remember the PI's name, but they
Was it in Berkeley or?
ultra cold rubidium experiments, and it's in the physics building.
Okay, great. What's your name again?
Debo Priyo. I go by Debo.
Dable.
Yeah.
Yes, well, thank you, Dable. I just noticed this is being recorded. So let me just update my statement that Duke is an outstanding institution. Please do finish your PhD there. I have a great colleague, formerly Princeton too, head of applied math, Rob Calderbank. And he is at Duke now. He's been there for, I don't know, 10 years or so. He's fantastic. And he actually worked, I think, with Peter Shore at AT&T Labs back then, Bell Labs back then, on quantum information. Yes, please.
This is Ashraf from Electrical Engineering. So in terms of an opportunity for the future, in some way, when we think about data in either for quantum machine learning or classical machine learning, it feels like a bloodless thing that is coming from somewhere outside, and you process the information and you get some results out. And it could be, this ImageNet and all sorts of that type of images. But increasingly data is actually generated by a society, social information, privacy, and other things that are coming from there. It could be done from manufacturing. It could come from business. And the places that have made the deepest impact are the places where they have bought into the loop and collaboration with those as business schools, the schools from sociology and philosophy about privacy issues. So I think in order to deepen and to make the next, take the next step, what is needed is not necessarily more of the same, because we'll always be follower if we do that. But to sort of take a new direction and deepen the discussion, deepen the provenance and an understanding of the data before we push them in the machine. So this, I think, there is an opportunity at Purdue, but Purdue is so big that it is also a remarkable challenge because essentially you can always find interesting problem just working on the technical side and a few colleagues around. How does one make these connections possible to deepen this field is something that probably is something we can think about. I mean, you can probably offer some suggestions.
Yeah, absolutely. Well, first, thank you for your leadership in innovation in semiconductors industry, microelectronics, something also extremely important to the nation and here at Purdue. I gather from what you just said, there were several interesting ideas there, one of which is understanding the data a little bit before you feed it. Now, maybe that's more about machine learning than quantum per se, and although quantum could be enabling and facilitating that machine learning and benefit from it in turn as well. Now, I guess the other side is the output of the machine be interpretable, understandable, and reverse engineerable as well. I think on the agenda, one of the earlier talks was related to that. So where is the human machine interface, right? And it's not just a matter of efficiency, but also is a matter of understanding, as you said. Now, some people have the view philosophically that that's the whole point, that you don't understand it, and yet it works better than the stuff that you do understand. So, skip parametric model, just go straight numerically, even prove theorems, right? And there is that philosophy, which I kind of agree with occasionally too, but then I guess it is more beautiful, more satisfying to look at the results and say, I also kind of now get it and understand it. I guess it's human learning from the machine there. And then another point you mentioned is, yes, Purdue is a very big place, and there naturally will be just longer physical distance and intellectual distance to traverse in order to collaborate. So we hope to tear down a few of those barriers and incentivize more cross-pollination. It's easier said than done, but again, the Quantum Science Engineering Institute has demonstrated both the feasibility and the benefit of that. Any other questions, suggestions? Things we're not doing well? Building what? Oh, the building I mentioned. Yeah, I'm not financing it, so it's easier for me to mention it. But yes, I agree. We do have to catch up for quantum, for microelectronics, for a few related material research and so on. That equipments are outdated and an expanded footprints is also needed. Yes. Yes.
So I guess from my perspective, there's a personal learning outcome on quantum and programming, and that tools are available. But we talked with some industrial partners. They're interested in actually building an educational platform as well within NanoHub to disseminate this material and make it not just for the graduate student geeks, but to actually infuse it also in undergraduate education where they can have apps that run quantum computers and they don't have to write a couple hundred lines of Python code to actually learn about it, right? So I think that's a great outcome. And if we can do this in other areas of machine learning and follow up on our land grant mission, we have a platform where we can do this and we can reach people that we normally wouldn't reach. So
you mean NanoHub?
NanoHub or hubs in general, right?
Yeah.
Whether nano is the big word or to me, it's the ability to reach people we normally wouldn't reach. That is the true impact we can have.
Yes. Well, on both workforce and a research community building, NanoHub is the most remarkable success over the past 20 years. And thank you for your leadership and congratulations on the renewal. But we got to think about the long-term success is like, Berk, we've got NanoHub that we are bragging about every day. Mark Lundstrom and I, wherever we go, we say, oh yes, we do have NanoHub. This is the best scientific collaboration and joint simulation. This is the Google Doc for getting actual things done, right? And it's good for education, it's good for research, but at some point we need to invest in the things we brag about as well continuously. So thank you for that leadership. And I hope you like the new research professor criteria as well. You got what you wanted, I hope. And it's a very good recommendation you gave to me and others for years now. Now, as to the point you just mentioned here, I'm sure you all have seen and used the Nano Hub and Hub Zero and other types of hubs. We've got Aeroastro faculty also doing Cislunar Hub and so on. It's a very powerful software tool and systems, and spurred us to create things like virtual labs and that turned out to be so useful 2 years ago and continuously. So the answer is yes, we've got to invest a lot more in growing it, in talking about it and embedding that. You know, I was just talking to Mark maybe 2 days ago to say, hey, use Intel Inside. If the brand is part of the logo, you cannot skip it, right? You know, I'm thinking like it will be powered by NanoHub, right? In all the propaganda materials we go out to give people. And if it's in the logo, then you know you cannot forget it. So we need to talk more about it. We need to have long-term plan for it ourselves or with private sector together. So we'll have more conversation on that.
Name, right? We have the new name already, NanoHub Q.
Q, okay.
Yeah, for quantum.
Okay. Q for quantum, Q for quality, Q for
quantum. Gerhard is a little bit too shy, and this is a good example what workshops like this actually could make, because our colleague, Professor Michel Lukin from Harvard, he co-founded company QERA, and they're about to make public their quantum simulator. And when he heard Gerhard's talk, he said, yeah, why don't we use it? And we would distribute this and make it available, because he has like 100,000 users all over the world. And he had, I forgot who suggested this name right away, NanoHub Q, quantum.
Mm-hmm. All right, just make sure we quickly get the website registered, the URL and all that. Now, I don't know if Young Chen is here, you know, is he in Denmark or is international collaborators out there? You know, if Charlie Marcus is watching this or watching a recording of say hi to Charlie. I saw him 2 years ago wearing a different hat in Copenhagen. And actually, I was a student. I also took Charlie Marcus class in electromagnetism. He was assistant professor at Stanford, and he actually gave us midterms and finals. So we actually learned a few things in that class. The best teacher, one of the best teacher that I've ever had. So you've got a great team and great set of collaborators. Any other suggestions? Well, I've got nothing else to do and can keep on going, but I know that you've got maybe refreshment or something. But I want to again thank all the organizers. Thank you, Sasha, for leading the workforce of this National Quantum Center. And I assure you, if I call for a faculty meeting, I would not have as many faculty as in this room right now from the College of Engineering. Usually it goes between a number between 2 and 3. So I really appreciate the chance to listen to you, and I jot down a few ideas in my head. We'll try to implement those as soon as possible. And thank you again for being here at Purdue. And I guess hail quantum, hail Purdue. Roll up. Thank you.
Thank you so much, Mom. Thank you for coming.
Thank you.
Thank you for coming.
Thank you for the invite.
With that, I guess we conclude our school. But before we all move into the reception, let's thank the real people behind the summer school. David, Blake, Thomas, Tracy, Sandy, Robert, and everyone who contributed. Round of applause, please, to everyone. Thank you.
Oh.
It was